Sure. Hello, good soul, everybody. I am Sibgha Anwar. I am a second year Bachelor's in Mechanical Engineering student, and today I would be presenting my presentation on our Martian rover, which is actually going to be a pressurized mobile habitat in which is able to sustain astronauts over a long distance, or it can enable long duration transverses in which astronauts can remain and practically live um in the rover. So let's okay. All right. So the mission motivation was actually that we want when we go to Mars, the all the things that we are going to focus on is exploration. We have to explore Mars. We have to see what's out there. So we need to have systems in which we can travel. So that is why I have worked on designing, or you can say a small like abstract on how we can achieve that. So in future, crewed missions require reliable long-distance surface mobility, and as we know that Martian terrain or Martian surface could be really unpredictable. There could be storms, there could be some rocky areas. Like the whole environment is really highly variable over there. And also the gravity there is also only 38% of Earth's gravity, so which increases different risks like rollover risks, and our system, or like our mobile system, can slip, or different things can happen to it. So we have to keep in mind each and every risk that could be involved in that. So we have to think about it and also make sure that everything goes smoothly when astronauts are inside it, because um, we cannot risk the life of astronauts. So vehicle must be able to sustain astronauts for extended period of times like days or even weeks. So the main problem statement is that Mars gravity is just 3.73 meters per second square, as I have already told that it is about 38% of Earth, which reduces the normal force acting on the vehicle. So basically what happens is, we all know about center of gravity. When there is less gravitational acceleration, that the center of gravity shifts, you can say it shifts upwards with all right, thank you very much. All right, continuing. The normal force moves downwards and increased slip, reduced friction coefficient, which basically makes the system more unstable while moving. So there is also like one thing that we have to consider is rollover threshold decreases due to lower stabilizing weight, because as the gravitational acceleration on Mars is lower than that of Earth, the weight is also reduced. You know, when a person here on Earth weighs something else, but when we weigh that person on Moon or Mars, he weighs lighter than he was there on Earth. So that's exactly what needs to be considered as well. And then there is one thing that is going to happen a lot on Mars, and that is terrain variability. There is going to be regolith basaltic rocks and slopes of up to 25 degrees. So those should also be considered, and the systems should be made in such a way that they can cope with all these factors. And also, vehicle must compensate using mechanical and AI stabilization, which I would be talking about in the next coming slides. Then let's talk about the proposed vehicle design. The dimensions are going to be 4.5 meters into 3 meters into 2.5. It is going to be the pressurized volume of the vehicle is going to be approximately 8 cubic meter for two astronauts. I have designed this for two astronauts only. There could be more if at maximum three astronauts can be sustained in this design that I am proposing. Also, the design of the whole rover, or like the whole mobile system that we are trying to build, is going to be radiation shielded. It will have its own integrated ELSS, and also the structural design would be optimized for reduced gravity loads. Also, and I am also proposing a design in which the frame, or like the hull of the you can say the of the mobile system, would be actually be designed in like a honeycomb composite panels, so that it can increase its strength, and also provide, like, if sudden weight or sudden force is applied on the like the hull, or like the outer part of the outer part of the mobile system, it could cope with it and it won't just collapse. Moving on, this is basically the internal design, which was kind of made last minute, but the front is going to have like a cockpit. We also need to enable our astronauts to perform EVAs, because of which I have added an airlock. An airlock, beside the airlock, is going to be the storage system, so that all the samples that are collected from the surface of Mars can easily and right away stored in the storage. Also, right below the storage, I have made so right behind the storage, I have made the lab, where a small lab where the maybe the astronauts can perform experiments on the samples that they collected. And then right beside it, there is a kitchen, and the kitchen will also have its own like small hydroponic system. Maybe if it is viable, we can put it there, or if it's not, we can just have stored items from the actual habitat that from where the mission was started. So there could be like packed and freeze-dried food in the kitchen, which the astronauts can use. Also, there is going to be a sleep and hygiene chambers right at the back, so that whenever the astronauts want to go to sleep, they can go to the back side and sleep there. Moving on. So the structural considerations include that we want to have like a lightweight composite hull. Hull is basically the outer part of the mobile system, which is going to be hollow from inside, and inside that, we plan on making some adjustments for internal radiation shielding, for which we can fill it with either regolith bags, or like some other material like polyethylene. Then we are also going to have like a reinforced frame to handle rock impacts, just like I talked before, that we can make like a honeycomb design that could help with that. And then we also need to take in make in take consideration of the lower gravity. So we have to make sure that we optimize the center of gravity to minimize rollover risks. Now, we also have mobility challenges on Mars. As discussed before, there is going to be less gravity, less traction, high rock density, and sharp basalt fragments. So, if there are really sharp basalt fragments, what can happen is the tires of our mobile system may get, or like mobile rover can get like punctured, but that would not be the case in this design, because we have made some adjustments regarding that I would talk about in the further slides. And also slopes are going to be greater than 20 degrees, which are going to be common in volcanic regions. Wheel shrinkage is going to be a huge problem as well, because there on Mars there could be some soft dust, and and like places where the wheels of the rover might get stuck or sink into the dust. And then we also have to consider that the temperature is going to change drastically, because of which it will affect the material's properties as well. So that needs to be considered as well. Moving on. All right. So, as problems that I have discussed in the previous slide, these are the solutions that I have come up with. This is for the wheel design. So, large diameter to increase first of all, I need to, we are going to increase the diameter of the wheels, which is going to be 0.4, approximately zero point 0.4 meter contact width with 0.4 meter contact width. So what this will do is this will provide a more stable place for the wheels, for the wheel rover to rest on the Martian soil. So it's going to be of a greater width so that they can easily float, or you can say easily move on the Martian soil. Then increased contact patch. It will so as the width has been increased, so the contact of the wheels with the Martian surface will give us a higher friction despite lower gravity. Although the gravity is going to be low, but due to the width of the tire, the friction between the tires and also the Martian soil will increase, which will again give us more traction. Then the problem that I mentioned before, that the basalt soil could be really sharp. For that, I have come up with the idea of using shape memory alloy in tires. One of the material that I came up with was nitinol. It is like a shape memory alloy. So after it is deformed, or it can, first of all, it cannot be punctured. So that rules out that possibility of puncturing the tires. So for that, we are using nitinol SMA, which is, say, SMA stands for shape memory alloy. So whenever it passes over a rock, it will be deformed. It will definitely be deformed. But as it is a shape memory alloy, um, recover itself and return to the same shape that it was before. So this includes high durability in it as well. So then it is going to be multi-segment. It will have a flexible mesh resist puncture from basalt. It will be designed to maintain traction on slopes and lose regolith. Moving on. So, suspension systems for low gravity. My basic idea was that also have to consider that the Martian soil is not completely plain. There are some areas which might be a little raised. There could be rocks. So in order to take care of that, I came up with the idea of giving independent suspension systems with high travel shock absorbers to each tire. So each tire will have its own suspension system and own shock absorbers. So it will tune the tuned. It will. They will also. It will. The shock absorbers will be tuned damping ratio for reduced vertical loads. Um, the active roll control system using IMUs and torque vectoring will be done. And also, I have decided that we can also involve AI into this, so that AI can take care of whether the front tire needs to work, or whether the previous tire is being affected by the terrain. So real-time adjustment the torques and suspension stiffness would be done, and this would be taken care of by AI. Then we also have stability in low gravity. So key adaptations that I have come up with is we will have a lower center of gravity. The center of gravity would not be halfway up. It would be lesser. It would be lower than the halfway up. So apart from that, the widest stance. Widest stance means that the tire's surface area, or like the contact area with the Martian soil, would be increased, and there would be active suspension would be done. Then there would also be the contact area optimized wheels, just like I have talked before, and also it would be AI powered predictive control. I will explain the AI powered predictive control as well. So what's going to happen is that AI is going to take care of um, the is actively going to take care of how much power is required to each wheel, how much power is required for each wheel to move through a certain terrain, and it will also do real-time terrain. It will analyze the terrain on which the Martian rover has to move on, and it will tell about each and every risk that is present in their path and how to how to overcome it. That would be done by AI, so it could be of great help. Then we have AI assisted navigation, just like I have just talked about. There is going to be real time terrain mapping, hazard detection, like we are going to see the AI is going to tell us about slopes, loose regolith, rocks. It will predict slip, rollover, and off center loads. It will adjust. In short, AI will be assisting with navigation, and it will actually be the one or be the thing that is going to move the mobile system or rover across the terrain. It will take care of adjusting the speed. It will adjust the torque distribution which is needed to each tire, and also the power allocation. Moving on, we are going to have, all right, so we have an ECLS system inside the rover. We have like communication systems inside the rover. We need to power the rover. So the power actually comes from this hybrid power system that I have come up with. We are going to use solar arrays, which are going to provide daytime operational power. So, well, the how that I have designed this rover is that it is going to move only through night. So the traveling is going to be just at the day, during the day, and at night it will just stay at one place to save power. And also astronauts are going to sleep at night time. They will work only during the day. So solar arrays would be there. They would be assisting with the movement of the mobile system. They would be the solar powers will give the all the energy which would be required to operate the rover during the day. Then they at night, what we are going to do is we are going to use radioisotope units to maintain the base load and also the thermal stability. So radioisotope systems are going to be active during the night, are going to be more active during the night, and they would be taking care of the ELSS at night, and also um, these sensors and communication systems that are going to be active during the night. So AI is dynamically going to allocate power to mobility, ELSS, and sensors. Then redundancy ensures operation during dust storm. So let's say that there was a dust storm and solar arrays got dirty and they couldn't perform well. So their radioisotopes come in and they help with the functioning of the rover and all the ELSS systems. Then there is going to be battery buffering. Battery buffering is going to happen, and it will ensure smooth delivery of power. And we also have mission impact and scientific benefit. This design is going to enable long-range scientific campaigns. It will support geological sampling in hazardous regions while monitoring stability systems include risk of mission failure. And hence it will enhance crews survival during extended transverses, and also it will strengthen future human Mars surface mobility framework. So this is going to be another next it is going to be the next step after reaching Mars. After we have developed a Martian habitat on Mars' surface, the next thing that we need to do is we need to get out of that habitat and explore Mars some more. So for that, this system is going to be perfect. So I'm going to conclude my presentation here. So mobility in low gravity demands mechanical and AI solutions. Um, and the terrain or the Martian terrain and Martian terrain is not the easiest thing to work on, or it is not friendly. In short, it's not friendly. So we have to keep that in mind and design our wheel and active suspension systems according to that to maintain stability. And also AI can be used in navigation to prevent accidents and optimize power. Then, and also we can also use design supports. We know that design supports science, resource access, and astronaut survival. So this system can play a really important role in Martian surface exploration. Thank you very much. That is it from my side, and I will stop.